Okay, so we're not going to finish this lesson probably. And don't worry about that because there's a copy of it in the grade 11 watch list, but there's also going to be a copy sitting in our online resources from a previous recording session. It's not that big a deal. But we've got this pulley scenario. And don't forget, we've got some promises that we're going to make to ourselves. Strings are massless. Pulleys are massless. And pulleys are frictionless. So obviously we are in territory of make-believe. The reason these are all important is because if the string had mass, then if there's more string on one side than the other, then it'll pull down on that one side more than the other, okay? Obviously the strings are also unstretchable. We talked about rigid systems before. The pulleys being massless is important because there's this thing called rotational inertia. And once a wheel starts spinning, it tends to keep on spinning. Kind of like linear inertia, right? We know this if you've ever turned a bicycle upside down and just spun the front wheel. It'll just keep on spinning. Don't stick your fingers in the spokes, right? Because it'll slice off your fingers. Wheels keep on spinning and they'll tend to keep on having that inertia. So the fact that it's massless is kind of a big deal to mention that. And the fact that it's frictionless, we mentioned already that friction in axles is a thing that slows things down. So this is a frictionless pulley as well. So we're going to say all those things are assumptions and we just kind of move on. In terms of our reference frame here though, the pulley systems are special in that they go around a corner. And so people typically talk about the tendency of a system to go to the right or to the left with a pulley scenario. In this situation, you can see that the mass on the right is 6 kilograms. The one on the left is 2.0 kilograms. So just in case you can't see it, 2.0, 6 are the masses for those guys in kilograms. And so this system is going to go towards the left or the right? The right, yeah. So we'll call towards the right positive and towards the left negative. And then when we go to draw our free body diagrams, what that means is that we have to make a decision. We've got force of gravity acting down on object 1. We've got force of gravity acting down on object 2. We've got force of tension. So we could say force of 2 acting up on object 1 and force of 1 acting up on object 2. And as soon as I do that, it looks like the action-reaction forces are pointing in the same direction, but they're not. Because this one to the left is down, and that's negative. To the right, up is positive. And for this one, to the right is down, positive, and to the left is negative. And so really, the reference frames are flipped. And we should be okay with that. Now, there are other people that say, hey, I don't like this. This is confusing. Why don't I just stretch the system out and think about it as a tug of war where one mass is pulling against another mass? In other words, gravity doesn't act down. We think of gravity as acting outwards, trying to tear the system apart. You know, like gravity acts this way, but gravity also acts this way, depending on which mass you're talking about. And that's a valid mental shift. It's just in that situation, we'd say to the right is positive, to the left is negative. I would say force of gravity acting on 1 goes that way. Force of gravity acting on 2 goes that way. This is a fine problem-solving strategy. It's just playing around with reference frames. Force of 2 acting on 1, force of 1 acting on 2. Okay, and so this kind of turning it into a linear scenario, or at least recognizing that going around a corner is actually linear, valid, okay, totally valid. Okay. Now, in terms of finding the acceleration of the system, the net force on each individual mass, and finding the tension in the rope, what we're going to be doing is essentially the same thing as the previous problem. What I'm going to do, just for the purposes of you having access, easy access on the YouTube channel to this, is I'm going to put this up on the screen pre-filled in, okay? And you can do your screenshots as necessary, but we can find the net force on the system by looking at the external forces, the force of gravity 1, force of gravity 2. That's going to allow us to calculate the acceleration of the system. Remember, mass 1 and mass 2 are the total mass of the system. Once we know the acceleration of the system, just like we've done previously, we'll take that acceleration of the system to find the net force acting on each individual mass. And then once we know the net force acting on each individual mass, just like Jake was suggesting, we return back to the original free body diagrams, and we can use that info to find the tension between the ropes. So I will post this as a video if you need to have access to it, just so that we can cap off the day, okay?